All right, hello everybody. My name is Alex Allen. I'm an engineering manager at Amazon's IVS, that's Interactive Video Service. I run our client engineering org. My co-presenter Kyle Lee, who did most of the work that I'm going to present today, can't be here today. So I'm going to do two things. I'm going to try to represent his team's work as best as I can, and I'm going to try to land this thing at exactly 15 minutes so no one asks me any questions. Product journey, we're going to start there, how we got to WebRTC, how we solved WebRTC at scale. It's a bit of a stretch. I don't know if you can ever solve WebRTC at scale. Quality of service, as always, and the future, mock and all those other things. All right, let's see how we got here. All right, IVS was born out of Twitch. So we started as HLS infrastructure, RTMP in, HLS out. That was built around Twitch's kind of latency requirements for building community. We sort of bended HLS to our needs to fit this model. And it was great, but it had a latency floor, 2 to 5 seconds or so. And that broke some interactive use cases that we wanted to pursue for new customers, things like betting and gaming, live commerce, etc. We needed real time. We experimented with a bunch of different technologies, including Warp, an early version of Media Over Quick. Shout out to Luke, who will be doing there you go, talk about this, and I'm sure we'll tell you the real story over cocktails later. It was great, but this is 2021. Web transport was still experimental then, and WebRTC was the thing that was available now. The only real catch is that it's not designed for the thing that we wanted to use it for. It's mainly designed for 2 people on a call and not millions of people watching a single stream. All right, so we basically built a real-time streaming system using Amazon's existing Chime SDK as our backend. We had initial product launch planned with our V1 that was very conferencing based as well. Right before launch, we realized this was not actually the product that we wanted to build and the product we could sell. So we rewrote the entire thing for V2 that was less conferencing focused, more broadcast focused. And internally, we were still relying on that Chime SDK as we built out our custom SFU, which is named Mercury. This freed us from a bunch of conferencing assumptions. And today we have a purpose-built system for WebRTC at scale for one-to-many. So how did we do that? As alluded, WebRTC can't scale. Everybody's heard this. I hear it all the time still at work. We're dumb, I guess. So we chose WebRTC anyway. And by the end of this quarter, we'll be supporting 1 million concurrent viewers on a single broadcast with WebRTC. We've actually, the main blocker here is really the plumbing, the operational plumbing, things like billing and metrics. But the data plane is really, the problem is capacity rather than architecture at this point. All right, here's your buzzword bingo start. So ICE, stun, turn, SDP, DTLS, all of these protocols exist to connect 2 peers over the internet, maybe behind NATs, but we don't really need to worry about that. We have a public internet, public server, public IP. It's unnecessary overhead. We can strip all of that out. There are a few problems still. WebRTC is kind of a clunky protocol, but it's workable. And there's no commodity CDNs for WebRTC. There's some economic problems, server density, content distribution problems, and then what architecture you might choose for your WebRTC system. The good news is these are more engineering problems, not really protocol problems. All right, so how do we solve server density? When we launched real-time, to make it a little bit more interesting to our customers, we launched it at half the price of our HLS product. And so we needed to at least match the HLS server performance. And at this time, we were running on a bare metal infrastructure, which meant we had finite capacity, and we had to close this gap. So you can see there, our HLS nodes were 60 gigabits per second, 13,000 users. Our initial WebRTC SFU was 500 users at 1.2 gigabits per second, which is a little bit of a gap that we had to close. So as any good engineering org would do, we profiled all the things. Our SFU was written in Go. We just assumed garbage collection was biting us, but that was like 3% of our capacity there. So that was not the main culprit. The main culprit was really UDP syscalls. Every packet was a context switch. That was our bottleneck. TCP is heavily optimized on the Linux kernel. UDP is not, unfortunately. But there are some solutions there, mainly DPDK, which I'll get into, which allows us to talk directly to the NIC and solve at least some of that bottleneck. And Kyle would like me to tell all of you that our SFU is the least idiomatic Go program of all time. So we are breaking all of the rules. Nelson maybe can attest to this after the fact. This is just a high level kind of architectural view. The main thing to take away here is kind of the split of the control plane and the DPDK data plane. Like I mentioned, we're a Go program. We're built around Pion. We handle the session lifetime, encryption, simulcast connection setup. All the core forwarding happens in DPDK. We're using ring buffers. We're not using CGO. There's some known foot guns there. And with this, we're able to achieve 12,000 viewers on a single typical compute-optimized EC2 instance. All right, second problem, content distribution. How do you get your media across regions? Obvious solution, you build your own CDN so that everybody can connect to the nearest edge. But we needed to cascade this video out. You can choose whatever protocol you want when you're talking to your own servers, and we looked at a few different things, including TCP and QUIC. Ultimately, what we settled on was a stripped-down version of WebRTC, WebRTC adjacent, we'll call it. So there's like no ICE, it does custom key exchanges, it multiplexes connections, and that allows us to have like one warm connection between hosts, which carry many different streams. So that setup cost is only paid once. Oh, and when we first launched this, we didn't have any relays, but this is a beautiful AI-generated diagram of what this largely looks like today. So publishers connect to the edge SFU nearest to them. There's relays with multiplex connections there. Then those connect to the subscriber SFU, which goes to the subscriber. The key thing here is like those cascading links are built on demand during SDP exchange. Warm path is faster TTV on joining. And then we aim to have only a single cascading connection between those hosts based on how many sockets we have available. Let's see. Third problem. Getting the right hardware for the right task. So an SFU in WebRTC lingo is a selective forwarding unit, which is basically our edge. An MCU, a multi-point control unit. It does it all, but it doesn't really scale, and they're expensive. So our solution was essentially a pub-sub architecture with server-side switching, which allows us to kind of choose our instance type based on the processing that we're doing. Turns out our edge servers don't have GPUs as well, so that's kind of an issue. This is what that looks like. So the transcoder is a subscriber to our stream, and it subscribes and publishes. So it subscribes to source, it does the decoding with its GPU, big expensive instance, it republishes N renditions. The SFU is doing all of the switching at keyframe boundaries, and it's switching from source to the transcodes seamlessly. As a result, the SFUs themselves stay relatively cheap. They're really just pushing packets, and then GPUs do whatever GPUs do, and we're not wasting money on big, expensive instances. All right, quality of service. If you're doing a video talk, I think you have to talk about QoS and TTV. So customers care, apparently, about QoS, and we've been working on a lot of different ways to make our QoS better. We've done a bunch of investments. We have experiments in progress today. So reducing the number of connections, GOP caching at the edge, which I'll talk a little bit about, a bunch of client-side optimizations, rewriting our Android networking stack, making latency configurable with a configurable jitter buffer, and then forward error correction as well. And let's see, right now it looks like our TM99 is right around 800 milliseconds for time to video. In this case, time to video is from connection establishment to the first decodable frame, and percent time frozen is less than 1%. All right, this is just a nice diagram of what that looks like. So we've got basically two recovery paths that compete for a time budget in the jitter buffer. We've got FEC, which costs bandwidth, but it's instantaneous. And then we've got NAC, similar to like how Quick works, which request a retransmission, but you're paying the cost in round trip time. And then the jitter buffer itself is customer tunable. So you can have a smaller jitter buffer, you get less latency, but you get more interruptions, or a larger jitter buffer, which of course increases time to video. And FEC in this case, we're primarily experimenting with Flex FEC. It's server side, it's enabled dynamically. If we have pressure or congestion, like we'll back that off so that we're not wasting bandwidth. All right. To start viewing video, you need a keyframe. And so we're doing a lot of caching at the edge of the latest GOP. The cache is always warm. When a new user joins and it goes through that SDP negotiation for WebRTC, we kick off a PLI, which is like a message to the encoder to generate a new keyframe. We merge those all together if there's a bunch of viewers joining at the same time so that there's only one. And then that's kind of racing that negotiation to have a keyframe ready as soon as the viewer wants to start watching video. So then where does that get us? IVS has a large-scale, low-latency system. We have real-time that scales and is continuing to scale. So other things that we're looking at media over quick, as many folks are. We're really just evaluating where this fits today, because it's a little different if you're looking at 30 seconds of latency as opposed to our low latency system. And so for us, it's a lot of conversations around like, what do our customers want? What gap does this fill? Could this replace a piece of our stack? Could this unify? And so we're doing a lot of evaluation there, a lot of experimentation internally, and we're doing a lot of experimentation with internal stakeholders as well. Multi-codec is something we've experimented with a lot over the past few years, from the publisher itself, like generating advanced codecs in a multicast scenario versus server-side transcoding. We've experimented with HEVC and AV1 support in WebRTC and our low latency stack. The goal is always better quality at equivalent bit rates, or just like better quality video is always nice as well. And then the final thing that we've been looking at, as a lot of folks are, it seems like, is agentic workflows. So because we already have this real-time system, we have the ability to like add subscribers dynamically. We're launching products to have AI agents that can subscribe to those streams, get data out of them, and then put data back into that stream as well. A lot of the conversations we're having with customers are around things like translation or moderation, that sort of thing. So we're working on enabling those scenarios in both our low latency system and our real-time system as well. Oh no, I thought I would have less time for questions, but that is it. Thank you.